Hello, everyone. And so for my master thesis, I work with Taina, a Professor Steiger lab in Bayreuth University. And we worked on a comparative analysis on stridulatory signals in bearing beetles. So just a brief introduction, because you heard it all from Taina already. But we know that communication is very important in parental care, and that bearing beetles from the genus Nicrophorus show biparental care, which is extremely rare in insects. And so both parents take care of their youngs. But what is also really interesting is that during their entire brood care, both parents stridulate. So it appears that they may be indeed communicating with the larvae. And if you look at different species, larvae rely differently on their parents for care. So there's differences in larval dependency. And for this reason, we took interest in their stridulatory signals, and we questioned whether these signals differ between different species and if this correlates with differences in larval dependency. This was our experimental setup. So we recorded 32 couples from 3 species, which are Nicrophorus vespiloides, Nicrophorus pustulatus, and Nicrophorus interruptus. And each couple was put in an acoustic box with a microphone, a camera, in a red chamber with just red lights for their entire brood care. And then we analyzed the recordings on Raven, and this is how they appear. You can see. This is how they appear on a spectrogram, so as a series of chirps, often clustered together. However, not all sound events look exactly like this, and by looking more closely, we could tell apart 2 different types of chirps, what we call single and back and forth. Back and forth because both if you look at it and also if you listen at it, I hope you can listen. It's not strong enough. Can we raise the volume? Do I try again? Okay, thanks. And this is the single one, and now the back and forth. So I hope you can appreciate the difference, but it sounds as a back and forth movement of the stridulatory parts. However, as you can see in the third picture, not always the difference is this neat, so that sound and looks as a single chirp with just a hint of return sound. So yeah, it's not always, sometimes the difference is actually more subtle. And the difference are not only regarding these, there are actually much more variation. First of all, variation in chirps duration. We classify them into normal, long, and extra long chirps. Normal because they are by far the most common, and they go from 0.04 seconds up to 0.30 seconds. And long chirps go from 0.31 seconds to 0.40. And all 3 species have long chirps, but Nicrophorus vespiloides only occasionally. And instead, Nicrophorus vespiloides can't produce at all extra long chirps. So it's only Nicrophorus pustulatus and Nicrophorus interruptus who does that. And the longest chirp I could find was 0.80 seconds. And here you can see an example of a 0.70 seconds chirp. Apart from this, other variation is that chirps can stand alone in small cluster or in clusters that are several minutes long. Then clusters can be very regular or instead inconstant and overlapping, as you can see in the upper picture here. And then we could potentially also classify clusters into loose, tight, or extra tight based on the average breaks length between chirps. And here below you can see a cluster which is clearly extra tight, so there's basically no breaks length at all between chirps. But I'm saying that we could do this potentially, and much more investigation are needed, because actually the 3 species differ a lot in their average breaks length, both between chirps and between sound events. So it's difficult to come up with a unified value that could count as an actual threshold for these categories. And so for all the signals I described you this far, it seems that all the species share them, most of them, but we could indeed find some sound events that are very unique for each species and clearly distinguishable from one another. So specifically, Nicrophorus vespiloides is the only one who has clustered this loose, and they sound like this. Nicrophorus pustulatus is the only one that has cluster instead very tight, the tighter clusters, and sound like this. And finally, also Nicrophorus interruptus has extra tight cluster, but they sound also very unique because the chirps are extremely short and fast. They sound like this. No, actually something was reversed. Okay, I can go on. But they should sound more. There is something wrong with the audio. Okay. And apart from those differences, we could also find some patterns that are extremely unique. So Nicrophorus pustulatus, and this is not occasional, this is a regular thing, they exhibit this pattern that we call blocks because, yeah, each block basically, and each block is composed of around 10 chirps, and each all block follow each other at a regular distance. And only Nicrophorus pustulatus has that. Instead, Nicrophorus vespiloides and Nicrophorus interruptus only occasionally produce a scratchy sound. It's like this. So, to sum up, do stridulatory signals differ between the different species? Yes. They have, each one of them has a very specific, unique sound event. However, except for them, they share most of the other signals, as you can see in the table, with some exceptions. So Nicrophorus vespiloides cannot produce extra long chirps or extra tight clusters or blocks. Nicrophorus pustulatus cannot produce scratchy sounds, and Nicrophorus interruptus cannot produce blocks. And we are currently working on the statistics regarding these pattern differences. Also, we will look at the activity variation, which will hopefully will give us some insights into the correlation with the larval dependency difference that I talked about first. And we will look also at difference in more specific sound parameters, such as the main frequency. And this seems, we're optimistic about this. Seems there's something there. So that was all, and thank you for your attention.